Welcome to the first of our videos in IB Chemistry this year, and we're going to review just a couple of basics first before we get started. Probably a bit of stuff that maybe you haven't thought about since you did junior science, but it's basically the fundamentals that we need to keep in mind when we start to talk about how molecules and compounds come about and how they interact with each other. So first of all, let's review what we know about matter. So when we talk about matter, we're pretty much talking about pretty much anything in the universe. So by definition, matter is made up of molecules, atoms or ions. So we consider it's made up of particles. We think about it's made up of small individual particles that we tend to refer to as atoms. It will occupy a volume in space, so it has volume and it has mass. And the other thing that we really need to remember here is that particles are always in constant motion. When we're talking about chemistry, we need to realize that nothing is ever perfectly still. Things are always vibrating or moving, twisting, turning. They always have some level of kinetic energy when we're talking about them. This is another bit of revision, so moving back to hopefully what we remember about solids, liquids and gases. So we used to, in year 7, we would draw solids as little arrays of squares of round particles, and we said that a solid would have closely packed, this is our solid up here, that it's closely packed together, so they tend to be quite dense, that they have strong forces between the particles, so they're strongly attracted to one another. They just vibrate in position. They have a fixed shape and a fixed volume. So then if we take our solid and we increase the temperature, so we add in energy, we end up with a higher energy state, and this is where we get to liquids. Now liquids, because they have higher energy, they move a little bit more. The particles are spread out compared to those of a solid. They tend to have weaker forces between the particles, which means they can move past each other and slide over each other, and they take the shape of their container. They still have a fixed volume though, so we can't really compress a liquid, but they do tend to flow and take the shape of their container. Again, if we add more energy, then we end up in the state of matter that we know of as a gas. And now we have something where the particles are very spread out, they're moving very quickly. Okay, so they have a large amount of kinetic energy. And they have negligible forces between the particles. That is, the particles don't attract each other very much at all. They tend to move randomly in random directions and quite rapidly. A gas has no fixed shape. It will expand to fill its container, and it has no fixed volume. If we open the container, then the gas will just spread out. If we crush the container, then the gas will compress down. So the thing that we need to start thinking about now as we move into chemistry is really the different levels of energy in each of those states, that moving from one to the other, if it's in a higher energy state, requires us to put energy into the system. And if we want to go to one of the lower energy states, so if we want to go back from a gas to a liquid, then energy needs to come out. We need to subtract energy from the system there, and usually that's in the form of temperature, so we cool the system down to remove energy from it. So when we talk about temperature, in most of what we tend to do in chemistry, we will be using these two here, which is degrees Celsius or Kelvin. So degrees Celsius is the temperature scale that you're most used to. It has the units of degrees C. We use it every day when we report temperatures of how warm it's going to be or how cold it's going to be. And it was based off the melting points and boiling points of water. So the melting point of water, the melting point of ice or water was determined to be 0, and then it was set at 100 for the boiling point, and then the scale was determined by dividing that number of gradations up into 100, and then each one of those was a degree. The Kelvin scale we'll see a lot more as we move on with our studies, and some of you may be familiar with it. But this was a scale that was designed in order to be able to describe absolute zero, which is the temperature at which all movement ceases, so when all energy is removed from the system. This is defined as negative 273 degrees C, which is absolute zero, and then it goes up from there. The size of 1 Kelvin is the same as 1 degree C, but it's just offset by this amount. So if we want to convert to Kelvin, we add 273 to our degrees Celsius and we get there. And as I said, we will practice that more as we move on. So a change in 1 Kelvin is the same as 1 degree C. They just have different starting points. The Kelvin scale starts at absolute zero rather than the melting point of ice. And then this is our conversion factors here of how we convert those. We won't need to use these for a little while, but it's a good idea to keep that in the back of your mind. So generally what we were talking about before when we change state is that when we change temperature, we can go through a state change. Remembering that when we go through a state change, it is a physical change, not a chemical change. That is, we're not changing the formula of any of the molecules or compounds, we're just changing how tightly they're bound together. So when I have water as ice or liquid water or steam, all I'm doing is interrupting the attraction between the particles in this. At no point am I actually stopping it from being water. So it's a physical change, and these are completely reversible. When I go from a solid to a liquid, it is called melting. Freezing is when I go back the other way. If I go from a solid to a gas directly, then we refer to this as sublimation, and carbon dioxide is something that you may be familiar with that sublimes. The reverse of that is deposition. Between a liquid and a gas, from liquid to gas is vaporization or evaporation. And then when we go from a gas to a liquid, this is condensation. So we often refer to condensation on a mirror or something like that when we've had a hot shower, and that's where the steam hits the cold glass and starts to condense and turn back to a liquid. If we were to plot the changes in temperature as these change of states occur, what happens is we have ice as we start to add temperature, so by adding energy or heat, the temperature will rise until it hits the melting point. And then at the melting point here, this is a mixture of ice and water. And what interestingly is our temperature will not change again until all the ice has melted. And then once it's all purely water, then the temperature will start to rise again. Once we hit the boiling point, it again will not rise temperature as long as there is a mixture of water and gas. So while it is boiling, the temperature doesn't actually change. And if we were to trap that gas and measure its temperature afterwards, if we kept adding energy in, the gas itself would start to increase in temperature. And this is what we refer to as the heating curve of water. And you may remember it from the ice to steam prac you did back in grade 7. Elements versus compounds, just a little bit more review. So we need to remember that substances that contain only one type of atom are elements. So this is oxygen, nitrogen, copper, aluminium, sulfur. Any of these are known as pure elements. But you'll notice they don't always have just one. We can have molecules that are elements, or we can have pieces of metal which form a lattice, which are also elements. As long as it only contains one type of atom, though, we refer to it as an element. Most non-metallic atoms elements form stable molecules or covalent lattices, and we'll look at those when we look at bonding a little bit later on. Some elements, such as the noble gases, are monoatomic, that is, they exist as single atoms, so they don't form molecules. So just a little bit of information for here. So this is sulfur, this is pure sulfur, the yellow crystalline solid that we see here, and this is S8 in its elemental form. Then we have carbon, this would be a piece of sodium, and then we have some copper here as well. So the elements that you should be familiar with that form molecules hydrogen, which is H2, so its elemental form is hydrogen gas, nitrogen gas, which is N2, oxygen gas, which is O2, then all of our group 17 molecules, which are our halogens, they are F2, Cl2, Br2, and I2, all form diatomic molecules as elements. The other ones that you may not have come across previously are phosphorus, which forms a P4 as an element, and sulfur, which forms these really nice kind of crown structures, which is known as sulfur S8, and they are the elemental forms. Make sure you make note of these because you are expected to know which ones form molecules. Compounds, on the other hand, are any combination of atoms that aren't just one type of atom. So it can be sodium chloride, it might be water. These can be covalently or ionically bonded, but they are mixtures of elements that have bound together chemically. Okay, so they've undergone a chemical change and they can range from small discrete molecules all the way up into large lattice structures. The last thing we need to review is our memory of compounds, mixtures, and elements and how we tell them apart. Remembering elements can be molecules or atoms, but they must be of one type of atom only. Mixtures are mixtures of different things, so they have different atoms, but they're not bonded together. So we can see here represented by the dots, we've got orange and green ones. We can see they're not bound together. So this is what we would call a mixture, okay, because they can be separated out. Okay, so generally we can separate out the different parts of a mixture into the individual compounds or elements that form that mixture. And then compounds have been chemically bonded together, so we can't separate them from each other without destroying that compound. So if we look at how we review matter and the final classifications of that, we can see that all things are made of matter. We can have pure substances or mixtures. Mixtures can also be homogeneous, which means they're the same throughout, or heterogeneous, which means that we might have a mixture of solids and solutions. So we would define ocean water as a mixture. It may have bits of sand in it, it's got dissolved salt and water, so it has different compounds, but some are solid and some are liquid, so it's not homogeneous. Whereas something like a glass of Coke would be considered to be a homogeneous mixture because the sugars and food colours and so forth are dispersed evenly through the solution. And we know that because every time we take a mouthful of Coke, it tastes the same as the last one. There's no difference. Then finally, with our pure substances, we can have elements which are pure substances, only one type of atom, or we can have compounds where they've been chemically bonded together, but all the substances made up of exactly the same compound. Okay, so that's it for our first video. Please summarise your notes and answer the quiz at the end of the lesson.